The Golden Gate Bridge stretches nearly 2.7 kilometers across one of the most violent stretches of ocean in the world. Its towers stand taller than a 70-story building. But here's the real question. What's actually holding this entire structure up? And what would happen if just one part of that system failed? Welcome to Loyal Engineering, where practical knowledge becomes professional skill. Today, we're breaking down exactly how this bridge was engineered, problem by problem. Before construction began, engineers faced one basic decision: what type of bridge could even work here? The channel is 2.7 kilometers wide. A beam bridge needs piers in the water, but piers this deep in currents this strong would be both dangerous and extremely expensive. An arch bridge would need to be tall enough to let ships pass underneath, which made it structurally complex and costly to build. That left one practical option: a suspension bridge. Two tall towers, a main cable strung between them in a curve, and a road deck hung from that cable using vertical suspender ropes. It's a design that avoids water piers entirely and spans long distances efficiently. But this design has a hidden problem. The main cable pulls on the towers with enormous tension. If you resolve that force, you'll see it has a horizontal component pulling the towers inward, which means, left alone, the towers would bend. Engineers needed to cancel out that horizontal pull. The most direct fix is to extend the cable beyond the tower and anchor it into solid rock on shore. To reduce costs further, designers also positioned the towers closer together, which shortens the unsupported deck span and lowers the tension the cable has to carry. There's a second problem most people never notice. The suspenders are steel, but the road deck is concrete, and concrete is brittle. Connect steel directly into concrete and repeated flexing will eventually crack the deck. The solution was to first connect the suspenders to a steel support structure, then lay the concrete deck on top of that. Steel-to-steel connections handle repeated stress far better than steel-to-concrete ones. The deck itself was built 27 meters wide, sized to handle both current and future traffic. Assembling all of this on site in constant fog and wind wasn't simple, so the steel truss members were prefabricated off-site and shipped in by barge. On location, cranes called derricks lifted each piece into position and workers secured the connections with rivets. A safety net was strung beneath the entire deck to protect the crew, a precaution that reportedly saved several lives during construction. Suspender cables were connected to the main cable at the same pace, and crews worked symmetrically on both sides of each tower to keep the load balanced. Once the steel framework was complete, crews laid wooden formwork on top, tied and welded steel reinforcement bars to the structure below, then poured and compacted the concrete using vibrating needles to remove air pockets and strengthen the pour. Now, here's a question. Is the bridge ready for traffic at this point? Not yet. There's still a major issue: thermal expansion. Steel and concrete both expand in heat and contract in cold. If the deck had been built as one continuous piece, a hot day could generate enough internal stress to seriously damage the towers and roadway. Can you guess how engineers solved this without compromising the deck's strength? The answer: they split the deck into separate sections and installed finger expansion joints at the gaps, interlocking metal fingers that can slide past each other as the deck expands or contracts, sometimes shifting more than a meter during extreme temperature swings. Smaller expansion joints were also added roughly every 15 meters, since steel expands slightly more than concrete, and this difference needs room to move even over short distances. One of the biggest design decisions was tower height, and it's more than just aesthetics. Picture two versions of the same bridge: a tall tower with a deep cable sag and a short tower with a shallow sag. Under the same load, which one holds up better? Less tension doesn't mean less stress. A shallow angle cable has to generate far more tension to support the same vertical load, which stresses the entire system. A steeper cable angle from a taller tower reduces that tension, but taller towers cost significantly more to build. Engineers balance these two factors, and for the Golden Gate, that balance landed at a tower height of 746 feet. Now let's look at how the towers themselves were actually built, starting with the harder side, the South Tower. Its foundation had to reach solid bedrock roughly 50 feet below the seabed, directly in the path of strong ocean currents. Divers first cleared the seafloor, then crews built a steel and timber fender wall around the work zone and poured concrete to seal it, pumping the water out from inside. But an empty fender wall under that much water pressure risks collapsing inward, so engineers built a reinforced concrete slab partway down first, letting workers dig beneath it safely as the whole structure gradually sank toward bedrock. Once it reached solid rock, the final reinforced concrete foundation was poured, with the fender wall left in place as permanent protection against the waves. With the foundation set, crews assembled the towers using hollow steel cells, riveted together in a modular, almost building block sequence. This cellular design kept the towers strong while limiting material and cost. Then came the main cables, and they're not solid bars. Each main cable is actually made of roughly 27,000 individual wires spun together on site using traveling wheels running back and forth across a temporary catwalk. Workers clamped and compressed the bundled wires with hydraulic presses, then wrapped them tightly in galvanized wire so the finished cable reads as one solid piece. These cables anchor into bedrock through massive steel strand shoes. Here's a real test the bridge faced. On its 50th anniversary, over 300,000 people gathered on the deck at once, far beyond normal loading. Can you predict what happens to a suspension bridge under that kind of overload? The excess weight caused the deck to sag by nearly 2 meters and put visible inward stress on the towers. This is exactly the failure mode we discussed earlier, an overloaded deck increasing cable tension beyond its typical working range. The bridge held. It wasn't damaged, but it's a clear reminder that suspension systems are engineered for a defined load range, not unlimited capacity. So, the takeaway is this. A suspension bridge isn't just towers and cables. It's a chain of engineering decisions, each one solving a problem the last one created. Tower bending solved by anchorage, brittle connections solved by steel framing, thermal stress solved by expansion joints. Every solution here depended on site conditions, load calculations, and professional structural review, the same process required on any real project. If this video improved your practical engineering knowledge, subscribe to Loyal Engineering and share it with another engineer. At Loyal Engineering, we help you build your knowledge, improve your skills, and grow your career. Knowledge, skill, career.